Okay, this talk has two components. One is that we'll think about periodic TASEP in all these solvable models that people were able to find a nice formula and then could take the limit, large time limit. These are done typically on the whole infinite space, on R or Z, like a TASEP, the usual TASEP, or as we saw in the another talk in the morning, that's on the half-line case. But nothing in terms of getting the exact formulas. There are other studies about, of course, but in terms of getting exact formulas, in terms of Fredholm determinant, and then taking the limit there, has not done too much about the periodic TASEP. So that's the one thing that I want to talk about here. And also another thing is that there's one-point distributions where the process in the spatial direction has been studied a lot. But on the other hand, the temporal direction, the joint distribution of the temporal direction is not well studied as much. So that's another thing that I would like to talk about, the multi-time distribution in the context of a periodic TASEP. So this is joint work with Zhipeng Liu. He's at the Krang Institute right now. It's based on 3 papers. The first 2 appeared in the archive, but third one is the one that's exactly what I'm going to talk about here. We are still in a preparation and hope that it will come out soon enough. All right. So to start with the general discussion, so in the KPZ Universality class, we know well, there's a 1-to-3 ratio, so which means that in terms of height functions, we take the following limit. So here's S is your spatial location and time is your temporal direction. You scale epsilon to the half, 1 here for the time, and then epsilon to 2 minus 2/3 for the space. In terms of the actual height, you scale by epsilon to the minus 1/3 and take epsilon to 0. Then you get a 2-dimensional process from gamma to tau to maybe some limit, right? Limiting the process. Maybe it exists, and we would like to know what that is. Of course, here when I write this one, here, I'm scaling around the origin in terms of space. But sometimes, depending on your initial condition, if it has a characteristic direction, then you have to travel along the characteristic direction and then scale nearby that point. But anyhow, so one-point distribution is well studied. That is exactly the duration of the distribution. With one-point distribution meaning that if you fix gamma and tau and then look at this as a random variable, that is in many cases trace-random distributions or they are variations depending on your initial condition. For the equal time case, namely if you fix your time and then think about the process from your position to the height, and there's equal time distribution it's been studied that it depends on the initial condition. For example, that is the area 2 process for the step initial condition, or the area 1 process for the flat initial condition, and some other initial conditions combined. Then we have some combinations of those or some other generalizations, including other things. And that limiting distribution, limiting process, so one-dimensional limiting process does not depend on tau. Typically, it has up to some scaling, different time slice. It has the same kind of process. It's proven for many cases, but it's also not proven entirely, right? So it's proven for TASEP and zero temperature directed polynomial models, like a less specific population model here. But it's not yet proven for many other things as well. For the ASEP, positive temperature directed polymorphs, and KPZ itself, it's still a big open question at this moment that actually to prove that the area 2 process and area 1 process arise from there. There are some progresses in this direction by, say, Nick Ziggurat has some work here, but still in the sense of getting the actual limit and getting the area process out of it is not done at this moment. Many people have contributed in this here. So I studied probably the earliest one was a prayer and response paper in 2001 around that time. And Kurt Johansen has a lot of papers there. And Sasamoto and Borodin and Ferrari did together with Fredholm, a series of papers in 2005 to 7, around that time. And also on Monday, we saw the other paper talk by Mathématiques and also Qualitative, when the initial condition is general, right, rather than the special step or initial condition, but flat or more general initial condition, and then they got this transition probability from general special location, special configuration to general special configuration. So of course, the work of Mathématiques and Qualitative view this as a Markov process, and then in principle that will determine your whole entire, if that's really the unique Markov process there, then it will determine the entire process. But that does not mean that we know everything about, say, if you fix a few points in time direction, what are the distribution functions of those joint distribution functions? Then we have to do another step of integrating out all the other random variables, which is not a trivial thing to do. So those temporal directions has been studied in multi-time direction. Oops, sorry. Has been studied in a few papers here. So here's some summary of the existing literature. So the fact that temporally the correlation should be at least t to the power 1 rather than t to the 2/3 in the special direction has been shown rigorously in terminology of the slow decorrelation by Patrick Ferrari in 2008. So that tells you that the temporally that the temporal correlation is much bigger than special correlations. Two-time distribution at two different times. The joint distribution was computed first by Dosenko in 2013, but that is not a rigorous work that is using a replica method. And furthermore, later work somehow dispute that validity of that work based on some other considerations. Mathematically, Kurt Johansson in last year, which appeared, computed considered Brownian directed less specific population. The less specific population directed, but it's a Brownian process version of that. For that particular model, he was able to compute the two-time distribution explicitly. Okay? So formulas in the end is a little bit complicated formula. It is a multi-series formula, but nonetheless, he was able to, from that algebraic finite form, were able to take a limit and show that there is a limit there, and then find some expression for that. Okay? And Kurt told me that he can further simplify the formula, and then maybe there are a simpler structure there, and maybe we can generalize to multi-time distribution as well. But that would be very exciting. So this is sort of the only explicit formula, and then the other two are more in terms of getting the bounds and so on. So Patrick and Herbert Spohn and last year considered the two-time covariance function, right? The fix your location, but take two times, tau1 and tau2, and compute the covariance and estimated how that behaves as two times are coming together or coming apart. Okay, short time covariance or long time covariance, and then got the decay of this covariance. Okay, of course, when time is far away, the covariance should go to 0, right? But the question is how fast it goes. Similarly, Bernardis and then Ladouceur considered tail of two-time distribution. So they computed the two-time, two locations, and then took x1 to be a large positive value, and x is fixed. So it's a kind of a one temporal tail, I guess, right? And then considered the case for the short time and the long time decay behavior. They used replica again, but also they gave a more heuristic, which seems to be mathematically plausible argument, but I'm not completely sure about that. Right. Okay, so given that, so this talk is going to be about we changed our model to periodic TASEP, and then we'll study multi-time distribution and try to get a formula for that. That's the goal of this talk. Okay. Any questions? Right. So, so I'm going to describe things in terms of height function. So we've seen this picture many times. So my notation is going to h of xt, the location x time t of the height function. So here's a general so you just look, if you look at the particle and hole, you put the valley, and on the other way around you put the mountain, and then you just follow through, and that is your height function as you exchange the particle. This configuration to this configuration, when the particle jumps, you change the value to the hill, right? So that's the growth process. Okay, and that's related to corner growth process as well. Now let me introduce the periodic TASEP, equivalent to period TASEP on a ring. So there is it's a periodic, spatially periodic. So there's a period. The period is I denote by L. So in this case, say L is say 6. Okay. And then so you put this down this in this 6 places, and then you put some particles, and you just copy them, right? So N is going to be denoting the number of particles per period. So there'll be N is 3 and L is 6 in this case. And the rho N over L is the average particle density. Particle density is just fixed number here. Okay? So we're thinking that rho is fixed, say rho is half, and then making L and N large. Okay? So we'll make the period large, and then the number of particle large, while the density is fixed to be half. And then we'll take time large. Okay? So there is a condition of how you are going to take a time large compared to the period being large. Now, if you think about if t is not too large compared to the period, right? Period is really, really large, and the time is not too large compared to that. Then, as you particles, and also and the particles are periodic. So if this particle moves, and then it's all copies are going to be moving at the same time, exactly same movement. So for a while, it does not feel its boundary, but at some point it starts to feel its boundary, right? So if it's on the ring, particle jumps through, and then it hits this tail of this, right, the other particles. So if t is not too big, then you're not going to feel this boundary effect. So therefore, it should be similar to infinite TASEP, and everything should be governed by KPZ dynamics. And we should see 1 to 3 scaling, and also we should see every process and so on, depending on what kind of initial condition you put. On the other hand, if t is really large compared to the period, then you are basically in a finite domain. So if it's a finite domain and time is really, really large, then everything is going to be mixing around. So it will eventually become equilibrium kind of dynamics, right? So at that point, your scaling and everything is not going to be KPZ scale, but rather equilibrium dynamics. So the fluctuation should be square root of t rather than t to the 1/3, probably. So there should be some crossover should happen. So when should this crossover should happen? The effect of equilibrium dynamics and KPZ dynamics. Around what time we will see this transition? So the spatial correlation, right? Spatial scaling is t to the 2/3, right? That's the KPZ scaling. So if t to the 2/3 is same as L, that means that all the particles are correlated to each other, basically. So then you are seeing there's a boundary effect, right? So t to the 2/3 should be order L, so that should be our crossover regime. So we'll call it relaxation time scale is t to the order of L to the 3/2. So that's the scaling that we are going to take in the asymptotics. So upshot is that in that scaling, the 1 to 3 ratio will still hold. It does not change. But however, the limiting distributions, the limiting processes will change from random matrix distributions to something that should interpolate random matrix and the Gaussian distribution. Okay. So periodic TASEP has been studied in several papers. For example, the Gua and Spon in 1992, they considered a periodic TASEP, and they basically looked at the operator for the Kolmogorov equation, And then they basically diagonalize that operator and trying to diagonalize the operator by looking at the eigenvalues, and then did some analysis of the eigenvalues, and then saying that, well, there's a spectral gap of a certain size, and they interpret that as the this relaxation time scale is the correct time scale, and from there they conjectured that spatial correlation in KPZ system should be t to the 2/3. And there are other works by Derrida and Leibovitz for the kind of really large time case where everything should be equilibrium dynamics, and then they got large division results. And there are more analytic results by Prijev and Pavlovsky and Golinelli and Malik in 1990s and early 2000. But those computations did not really yield to a formula for the distribution itself. Okay, those are more of computations of computing the eigenvalues and eigenvectors of the Bethe operators. Through the 2013 and 2016, Prolak did some serious computations, and he was able to compute basically all eigenvalues of this Bethe operator, ansatz operator, and so more or less he diagonalized the entire operator. And then furthermore, in this relaxation time scale, and then he was able to combine them together and then they rewrite the sum in terms so that he was able to get some Fredholm-like formula for the actual distribution itself. Okay, so that was a pretty strong computation that he did. But there are some missing mathematical proofs, but the final results looks pretty interesting. Okay, I'll talk about that a little bit later, a little bit more in a few slides later. Right. So I'm now going to state the results for the periodic step initial condition for the periodic TASEP for this special initial condition that I'm going to explain in a second. Okay, after presenting that, I discuss some how it's computed. Okay, so we'll start with the periodic step initial condition. So it's step initial condition, but it's periodic model, so it should be periodic, right? Okay. So what it means is that there are a bunch of particles at the initial, as an initial condition. There are a bunch of particles together, packed, and then empty. So that's in the one period, and then it's just copied. Okay. So step, but periodic. And then goal is to compute multi-time, multi-position. So I'm going to present multi-time, multi-position joint distribution in that limit, the relaxation time limit, the critical time, when t is order L to 3/2. And then for the special case of one-point distribution, I'm going to discuss one or two properties. For the other initial conditions, like flat and stationary, one can also do that in terms of one-point distribution. Okay, not the multi-time, multi-position, but one-point distribution one can do. Prolak and also myself and Zhipeng Liu did this one independently around the same time last year. Okay, but I'm not going to talk about these things, but just the step initial condition today. Okay. Right, as I said, so time period, number of particles all go to infinity. The density of the density will be fixed. For convenience, let's just say half. Okay, we can do other general rho, but just half for convenience of the presentation. And then time is going to be L to 3/2. Okay, so I just want to say now that unlike the just step initial condition in the infinite TASEP on the infinite space, because here's a density, initial density is going to be 1, 0, 1, 0, 1, 0. So there are shocks, right? So there are infinitely many shocks, and one may have to do something about that. Okay, we don't have to do much about it, but I just want to mention that. So we are going to compute the joint height distribution. Probably that is height at Sj and tau j, Tj. So Tj's are different. It's less than some height function Hj. So I'm going to scale the position Sj to be gamma j times L. Okay, so the position, because of periodicity, the position you only have to look at the 0 to L interval. So gamma j's can be restricted to between 0 to 1. And time-wise is tau j, 2 times tau j to the L to the 3 halves. That's the scaling that we are talking about. And then I'm going to assume that they are ordered, and they are all distinct as well. In terms of height, there is a average height speed, half tj, and then scale by L to the 1/2 for these fluctuations. Okay? And that's the variable xj. Okay? So the powers here is L, L to the 3 halves, L to the 1/2. So power 1, 2, 3, right? So, okay, so the same scaling as the KPZ scaling. Okay, so the theorem is that if you take that for any fixed m, any fixed sj, tj, and any fixed gamma j, tau j, and xj, the joint distribution will converge to some limit. Okay, I don't know whether this is a limiting distribution, but there is a limit. Okay, so let me describe that distribution. It will take a little bit of a few pages to describe this limit. Right, so the formula looks like, so I suppressed the dependence on the gammas and taus. So that is a multiple integral. There is m-fold integral, and there are two functions, c and d, and then the variable z1 to zm. And the contours are nested contours, circles, say, and then of radius less than 1. And CG and DG are explicit, and CG is some explicit function I'm going to explain in a second. It has a simple poles when the Zi and then Zj's are the same. On the other hand, the DZ is going to be a determinant, Fredholm determinant. It has an isolated singularity at the Zi at the origin. Okay, and CZ is of this form. So here's a form that gives rise to simple poles when the conjugative things are same. So here's this is only Z1 and Z2 and Z2 to and Z3, and those are the only conducting connected. Here's AI, depends on only Zi. The AI is given by, so here's X, here's tau, and then given by the polylogarithmic function. Okay, on the other hand, finally, the Q is some analytic function. It's very explicit. It's given in terms of, again, another polylogarithmic function. But it doesn't depend on the parameters, x, tau, and gamma. And also, it's non-zero at 0. So Q is some kind of harmless function that has to be added to it. Okay. Right, so some explicit formula of C. And then for D, which is this Fredholm determinant, so I have to describe this kernel K, operator K. So this operator lives on discrete space rather than continuous space. So if you remember, if you know it, if you remember the formula, probably or everybody knows, I guess, if you remember the Fredholm determinant formula for the trace rhythm distribution, which should be some kind of analog of this in at least one point case, its contour is a continuous contour, right? Either some part of real line or a complex contour, depending on how you formulate it. But here it becomes discrete points. Okay? That is the reflection of the fact that it's a discrete problem rather than real line problem, whole line problem. So instead of using Fourier series transform, you're kind of using Fourier series in a sense, and then there are all these discrete nodes rather than continuum curve. So the K can be decomposed into two parts, K1 and K2. And then the discrete space they live on is defined by the zeros of the function here. Okay. So let me just go back one more page here. So this D depends on these external parameters, Z1 through Zm. So those parameters, so if you pick any one of them, if you take Z, complex number, less than 1, modulus-wise, and if you look at this equation, and then think about all the zeros. Okay? So when Z is less than 1, then the zeros are here. Okay, so that's not the zeros. As Z varies if z becomes larger but smaller than 1, then these will come closer together. And z becomes small and going to 0, then they will be far away from each other. Okay, so take those roots, and then let's look at, denoted by LG, these left zeros, and RG, the right zeros. And then this, the first operator K1, when m equals 3 case, lives in a space, little L2 of RG1, L2 of LG2, little L2 of RG3. Okay, so left, right, to left, right, left. Okay, so schematically, they are coming from these white dots to black dots. Okay. All right. And then the kernel now. Now, kernel has a block structure. So m equals 5 case. The kernel has, the K1 kernel has 2 by 2, 2 by 2, then 2 by 2, 2 by 2, 2 by 2, and then if there's cannot fill the 2 by 2, it becomes 1 by 1. Alternatively, the K2, the other operator that has multiplied, will have started with 1 by 1 block and then 2 by 2 block and down the road. And finally, now I have to describe this, what kind of things are in this kernel explicitly. Okay, so if you look at the just 2 by 2 block here, I can write it as a 2 by 2 block matrix kernel. There's a Cauchy block, and then there's some kind of diagonal functions which are kind of harmless. They do not depend on the parameters, and they depend on z and z prime, z1 and z2, but not the parameters. And they are kind of given by another polylogarithmic function. The polylogarithmic function comes in here because of the this periodic nature of the problem. The important thing here is that this is fi minus 1, fi plus 1. Okay, so here's if this is a block given by index I and I plus 1, I minus 1 comes in here to link this block to the previous block. And then the other ones are I and I plus 1. Okay, so those are in this function here, e to the tau w cube, gamma w squared, and xw, which is a standard form in the Trash-Widom formulation, or any other Airy process or Airy-1 process computations. Okay, right. Okay, so they already did this. So I'm going to describe the one-pointer function briefly, and then talk about the proof.
So this formula was known before, or this is?
I don't think it's known.
This finite time formula is also part of your because you were describing other people.
Oh yeah, this is our work. Sorry, yeah. So it was maybe not clear. So the result is the result of.
Well, I thought maybe the limit or something. The whole formula is new.
That's right. So this formula is going to be a limit of a finite dimension, a finite time formula. That's a part of computing this. Yeah, it's the limit. All right. So for the m-point distribution, we don't have the how it behaves really well enough. But for one-point distribution, it behaves as it should behave. Okay? And then we can check that from the formula. So we didn't really prove it, but the formal computation from that determinant of the formula, one can show that when tau becomes 0, so tau was a rescaled time parameter. When time that goes to 0 means that we are going to the KPZ dynamics, and therefore the one-point distribution should go to the just KPZ, the KPZ case or the infinite TASEP case, namely the FGUE. Okay, but there's FGUE squared sometimes happens depending on your spatial location due to the shocks. Okay, so there are shocks some places, and due to the shock, sometimes you have FGUE squared. So I'm going to explain that in the next page. On the other hand, when the rescaled time parameter tends to plus infinity, then you are going to go to equilibrium dynamics, and you should have your fluctuation given by Gaussian distribution, normal distribution, rather than the Trash-Widom, and that's what you can see from here. And then the formula is reasonably good enough to be able to plot some graphs. So this is supposed to be Trash-Widom, this is Trash-Widom square, and this is supposed to be Gaussian. Okay, so in terms of that, the shock, so if this is our initial condition, so 1, 0, 1, 0, 1, 0, and so on, so on. So in the hydrodynamic limit, if you just run the time, that's in the intermediate time step, it looks like there are some discontinuity jumps. Okay? And as time goes on, these jumps will getting smaller and smaller. And here there are some jumps, but it's kind of invisible. And this is supposed to be the relaxation time scale, and this is super relaxation time scale, and time is really large. So one can check that this continuity is of order L times t to the minus 1. In the relaxation time scale, when t is L to the 3/2, or L is t to the 2/3, so then this becomes order t to the minus 1/3. Right? Okay, so then that is the fluctuation that is corresponding to high fluctuation, and you cannot distinguish whether that jump is really global jump or coming from the fluctuation itself. So then you sort of lose it. So what is known is that in the step initial condition or any general initial condition, along this kind of away from the jumps, one should get trace rhythm, but exactly at the this continuity point, one should get this trace rhythm square coming from one side have some fluctuation, the other side has other fluctuations. These two fluctuations are competing each other, and whatever higher that you get. So your max of two trace rhythm distributions, and that was discussed by Ferrari and Neja in the situation of infinite TASEP. Okay. Right. Okay, so very brief discussion on the proof for the finite time formula. Okay, so so the limit is obtained from an exact finite time formula, which has a parallel structure. The entire structure is there for the finite time. So it is block structure and C times the determinant, and there are multiple outside integrals are all there. So the way that we proceed is that instead of looking at the periodic TASEP, it's enough to think about TASEP in this configuration space. So the particles are x1 to xn, but xn should be less than xn plus L, right? That's the V1 period, right? So if you're the first particle there, you should be less than your last particle, but moved to the period, the identical copy. So in the usual case, we don't have this last condition, but this is extra confinement. Okay. So we proceed with the coordinate Bede-Ansatz method, okay, which is developed, applied to the TASEP case by Schutz. He computed the transient probability for the TASEP explicitly in terms of some determinant formula. And then later, Rakos and Schutz, using Schutz formula for the infinite TASEP case, reproduced the Johansson's result, right, which is the Fredholm formula for the one-point distribution for the infinite TASEP. Of course, knowing the answer, it was how they were able to produce, but without knowing that, it's quite difficult to get there, but they were able to do that. And then further down, in around 2007 and 8, or maybe around that time, Borodin and Ferrari, Preoff, and Sassamoto, starting using this Schutz formula, obtained various Fredholm determinant formulas for equal time process for various different initial conditions, right? So that just, they developed this machinery extensively. Then Konstantin, this talk on Monday, you start from that formula, right, and then get for each initial condition. And furthermore, and Tracy Widam in 2008 and 2009, there are a series of papers. They take this one and applied it to ASAP, and they were able to compute the one-point distribution for step initial condition, and of the other cases as well. Okay, so we are going to use this technique. So there are 3 steps in the proof. So step 1 is to compute the transient probability explicitly. So that's a kind of finding the Schutz formula. So for when x and y in this configuration space, we want to compute the transient probability from y to x in time t. So here's a formula. How we read this formula? So there's outside integral dz. Inside is n by n determinant. And there's a sum inside. So this sum is over the roots of the following equation. So this algebraic equation, given z, I look for w satisfying this algebraic equation, polynomial equation. There are L roots, and these are the roots that I plotted. Depending on z, size of z, they can be in one of the three possible positions. Z is less, absolute value z is less than some critical number. They are separated in two parts. At critical z, they are in some kind of self-intersecting loop. And if z is large enough, then they form one big contour. Okay? So what you can think about here is that this, because it's a sum, then you cannot do any contour deformation. The outside integral is what allows you to do contour deformation. As you vary your z, you can make this w on these zeros either shrink or expand, right? So that is your contour information. That's the freedom that one can have. Okay, how one can compute this? I mean, this is the analog, direct analog of Schutz formula for the infinite TASEP, in which it doesn't have this outside integral, and this summation is basically integral, okay, which one can obtain by just taking L to infinity, the large period limit, and that has exact analog of the variation of that. How you solve this one? How you find this one? Well, you're basically looking at the Kolmogorov-Ford equation, and then bang your head and try to solve it, right? Okay, and then of course, if you just bang, then you cannot solve. But people have developed the machinery, the coordinate variables, then there's guidelines what you should do, right? So Kolmogorov-Ford equation is a basically linear equation, but not constant coefficient due to this delta interaction. And the method is how you can deal with this delta interaction. Okay, you basically remove this delta interaction, but they put that condition into your boundary condition in your PD system. And then there are some methods that you can follow through. Okay? Right. And then the second step would be, okay, so it's like a Markov chain class in the elementary class. You take that transition probability, then you actually plug into your summation formula and try to sum it. Okay? Right, so you have this joint distribution here. So going from y to time 1 at some configuration, and the next time step, t1 to t2, from that configuration to go to the next time step, and so on, so on, so on. But then I have to sum over all possible configurations in such a way that if I look at the, say, xi part, which has its coordinates, I have to sum over all possible locations of the particles, right, under this configuration space condition. And also, my particle should be, kith particle should be bigger than ai, so that's extra condition. Okay? So one has to do that summation. Okay? So that's the tricky part. And the key part is that that sum turns out to be rather doable. Okay? If you ask me why it was doable, I cannot answer. I don't know why the proof works, basically. My feeling is that this condition that xn is less than xn minus 1, x1 less than xn plus L, you can just move them around. It's the same as xk is less than xk plus 1, right? Then x1 less than xn, xk plus n, right? So there's a kind of symmetry. So then the first condition that xk is equal to a is same as just a, all the other terms less than a plus n. So that's a symmetry between these particles, and somehow that is helping our computation extremely. Okay, we are using that several places. But that's the only explanation I can give. But nonetheless, well, once you do that, okay, so if I just go back one step here, so there's outside integral, there's a determinant and sum. So it will be, each term will have integral and determinant. Each determinant has a sum. So that integral come out to this. And then there is a determinant of a summation, then you exchange the summation and determinant. And then you reorder your summation of this outside and inside, and then try to maintain that. And somehow it becomes this rather simple formula. Here C is some explicit function, but the dy is the important thing, which is a determinant of size n by n. which come up to be relatively simple formula of this one. Okay. So then the initial condition y is there, yi. Okay, and then so step 3 would be take a special initial condition and hope for the best, meaning that hope that this really simplifies things. So you take yi to be 1 minus I, so that's the step initial condition, right? So ith particle is starting at 1 minus I. So if I put that in here, yi is 1 minus I, then this term cancels out, right? So we are lucky, right? So this cancels out. And so we end up with just this kind of structure. And then the rest is showing that, believing that this can be done, and then try to prove that this is actually Fredholm determinant. So there, what one has to do is that in the previous computations, the outside integral can have arbitrary size. Well, now we have to restrict our contours to be smaller than R naught, such a way that all the zeros are of this type rather than the two pictures. Once you have pictures like this, then you can count which particles are on the left and which particles are on the right. And then for the right particles, we have to use the whole and particle exchange, duality. Okay? But somehow that helps in terms of computing the Fredholm determinant. And then one has to reduce this one to that formula. Okay, so I've got 1 or 2 minutes left. So here's a slightly longer discussion. Okay, so okay, in this slightly longer discussion, I'll just point out just one lemma, technical lemma. So in the middle of the step, in the step 2, which is the difficult part, one has to do the following summation. As I mentioned here, the sum over the particle configuration such that the kth particle is bigger than A, and then some product of two determinant. Okay. So if this periodicity is not there, then I'm not sure how easy it is to compute this determinant. Maybe easy, maybe not, I don't know. But in our case, due to the periodicity, one can compute this determinant rather easily, and one gets some, that determinant come out to be, that summation come out to be this single integral, which is Cauchy type. Okay, that was one of the key lemma that we have to use, but somehow once that's done, the rest one is somehow more or less, okay, one can do the rest. Okay, right. So sorry that was not very clear how it's done, but I think, yeah, I could not do. Well, probably I can do that better next time, but this is all I could today. Right. Okay. Thanks for your attention. Leonid, Leo.
So do you have access to time-like joint distribution in this way?
Yeah, that's right. Yeah. So this arbitrary time direction, but for the periodic TASEP.
So do you get access to multi-point slow decorrelation type?
Okay, so that will be, can we use this formula for anything, right? Okay. I don't know yet. We just got this formula, and some things, okay, it's hard to say whether can you do like a decoloration when the tau 1 and tau 2 becomes large. Can you get that? Or when tau 1 tau 2 becomes close, can you reproduce the results of, say, Ladouceur about the tail decay? I mean, formula is some features that I can see, but it's complicated enough that I cannot see that I can do that right away. Yeah. I'm not sure at this moment.